Welcome to Retro Upgrade. This time we'll be taking a look at a capture card that failed on me. It's a cheap one. It's one of these USB 3 capture cards that capture in 1080p and the input is max 4K 30 frames per second. These are quite cheap, they're €6 each. This one failed on me when I was recording the GBS-C episode. And I think it was the constant switching of the GBS-C when it didn't find sync and it fried the chip on top. Okay, let's check out what it does. So it fails immediately when you hook it up, and then it shows an error in the device manager. Okay, so let's do some testing, see what's wrong with this thing. These are quite cheap, usually not worth fixing. So I hook it up and check with the thermal camera to see if I can see any excessive heat buildup. This is a metal casing, so it should dissipate some heat. It's getting up to about 60 degrees at max. So that's pretty high for an enclosed system like this. A visual inspection of the connectors just to see if there's a short somewhere. The HDMI connector seems fine. You should always do this because the pens can bend inwards. This is a USB 3 connector and also looks fine, no bent pins. So it's probably an internal short or something that's preventing it from starting. There are some caps that can go bad and go open or shorted. Okay, so these are quite hard to get into. These are mostly sealed units and are actually not meant to be repaired because they are so cheap. But the curiosity got the best of me, so I wanted to see what's wrong with this. First, some light prying with some spatulas I have. These are metal spatulas. Unfortunately, this seems to be glued, so yeah. This didn't work out very well, but on to the big boy, the heat. I'm using 100 degrees C. You can see I damaged the cover a little bit, but that doesn't matter. I was not planning on reusing the casing anyway, but if you're going to do this, use the heat immediately so you don't damage the port, actually. The piece of paper is so I don't burn myself, because this is all metal. It's actually transferring quite a lot of heat into the casing. And that actually is one of the things you can actually do to prevent this. You can open this up and put on a heatsink on the little chip that dies. But that's a little spoiler for the what's wrong with this thing. Okay, so I just pry a little bit at a time and you will finally get there, because the glue will get loose. And you can only pull it out from the side of where the cable goes in, because there is a small opening on the other side. You cannot pull it out from that side where the HDMI goes in. Now a quick word from our sponsor, PCBWay. They have extremely affordable pricing. They have a lot of services to choose from, everything from PCBs to 3D printing. They also have an incredible support staff that's really kind and helpful. They also have the incredible shared projects page. Give them a try. Go to PCBWay.com and make your first order now. Okay, back to the video. Okay, so as a quick visual inspection. Okay, we can see the problem immediately. The chip has a hole in it. And this is on the USB side, it blew up. So, and looking at the trace, it goes to the plus. So that's probably a power trace. So the power in from the USB plug burnt it out, probably over current, because it switched resolutions all the time. But I'm not really sure, but these are notorious to actually overheat these small chips. There are a few tips online that you should drill a hole on the casing and put a heatsink on this thing. So yeah, considering this is a metal casing, That should be done from the factory, but yeah, oh well. Hindsight, I guess. Okay, so let's do a quick test to see what happens if we hook this up. I sped up the video here so it heats up. And it's getting quite toasty immediately. As you can see, over 120 degrees. And this is the chip side right here. And yeah, over 120, and that's the max my thermal camera can do. So yeah, this is completely dead. Now we need to make sure it's the chip that killed itself and not another component like maybe a resistor or something. But first, let's check the schematic or the datasheet for the chip. So it actually inputs up to 4K, and checking the datasheet, it's actually showing that it's USB 2 and not 3. So that's quite deceptive because it uses a USB 3 plug with the correct connectors inside. But checking the datasheet a little closer, yeah, it only outputs USB 2.0. So it's actually completely useless to buy the USB 3 version that costs actually a couple of euros more. The chip seems to be quite capable. It inputs all the way up to 4K 30 FPS and always outputs 1080p, or yeah, everything up to 1080p to be more precise. But they're quite handy to have. I actually bought the more expensive kind that cost about 25 euros that are bigger, but they are probably based on the same chip. But they do have a bigger casing, so they don't overheat as easily. So yeah, no, and I checked online to see how much these chips were, and they are, if you just buy one, it's too expensive. It's like 7 euros each. And considering the capture card is about 4, it's not really worth it. Don't spend your money on the USB 3 version. It's not worth it because it's the same chip and it's only USB 2. So go for the USB 2.0. It doesn't matter. Even if they say resolution differences, there are none, just so you know. They say max 30 FPS. If that is the case, it's probably just software, nothing else. Okay, so just for curiosity's sake, because this is not worth fixing, this is a good example of object that's not worth fixing. For what's it called, to learn how to fix stuff, yeah, it's viable, but not really economically viable. Okay, so let's see what's wrong with this. So to find out what killed it, we remove the chip first. So I'm using my special homemade splooge flux here. And I'm applying about 300 degrees with hot air just to remove this quite easily. There are a few failure modes here that could happen. One of them is a diode goes short, kills the chip. But there is no diode on the line that actually exploded, so that's a power line. It has a small fuse. I checked the fuse, it's fine. So the only thing left is maybe a short in the power system. It gets 3.3 volts from a small regulator down to the left. We'll be checking that a little later. Also, there could be maybe a capacitor or something that went short as well. So you have to check that as well. I'll be showing exactly how I do all the steps here, so no worries. This is just for educational purposes only because it's not worth fixing. Pretty much just buy a new one. This is a good example of knowing when to quit. The curiosity got the better of me, so I recorded this part as well because I wanted to know if it was the chip or something else that killed it. Because these chips could actually be useful for some other projects I have in mind. So it has a big ground plane underneath, so that made it a little harder to get off, but eventually got there. If I had a preheater, it would be a lot easier, obviously. Okay, so a little blurry, sorry. There we go. But this looks pretty decent. Now you can get a close-up of the exploded trace. So that looks to be in the power in, but they crisscross a little bit inside the housing. Maybe it's another rail that exploded, so it's a little hard to say. Okay, sorry for the shaky cam. Okay, so we're back. Now, time for some testing of components. This is a part that was not necessary really, but yeah, for science. Okay, so I'm checking all the capacitors first, from ground to, and checking if they are shorted on both sides. If it beeps on both sides, something's wrong. I'm also checking the regulators and the chips, the ones that I know what they are. In some cases, I have to check the data sheets to know exactly what they are. For example, the regulator, I wasn't sure about the pinout for it, so I had to check online. But that's the way you actually troubleshoot stuff. You don't know how it actually works. You look at the data sheets. Hopefully this is somewhat entertaining to watch or helpful. And now you know how to prevent this. Just open it up, drill a hole where the chip is, put on a small aluminum heatsink on it with some decent enough heatsink compound, and you should be good to go. This died due to overheating, 100% sure. Okay, so let's see. So this is the regulator, and I'm just checking to see if there are shorts in between all the legs, and only the ones that are shorted will the big tab is shorted to ground. I was guessing, so that's usually the case for these. So I'm checking the data sheet right now. And I just want the pin out. So it's a 5 volt to 3.3 volt. So it's exactly what I expected. And there's the pin out. So you have the numbers on the actual drawing. And then you have, to the left, you have the explanation of what they are. Just checking a little further down just in case to see if there is a recommended build for these things. They usually have an initial design document on how to use this thing. I'll probably be using these regulators in the future on my projects as well. Okay, so 1 is ground, 2 is V in, and 3 is V in, V out. So 1, 2, and 3 from the left. So I was correct on assuming the big one is ground. So we need to check the V out. Okay, back to the board. Okay, so I hooked it up to the computer now, so I get power into this. I'm checking out to see what causes the tearing in the picture on the microscope. It probably is too slow to send over the image completely, so it tears a bit. But there is a way to mitigate it. I just have to check a few options at the moment. I don't know how. Oh yeah, you saw me put some marker on the chip. I used a red marker to highlight the text, so it shows up better on camera. You use the marker, and then after a while you rub it off like I do now, and you see the text really clearly. It's a tip you can get if they filed off their markings, for example. It works most of the time. If they used a laser engraver to cover the markings, you can't see them, but in this case it helps a lot. It's And it's a helpful thing to know, actually. Okay, so let's check the voltage. I'm on ground. So we check the tab. Yeah, nothing as expected. Let's check the third pin. This is the center pin. That should be 0. That's fine. No, I'm on beep mode now. Sorry. Me being stupid, obviously. I'm just checking for shorts. Middle pin and V in are shorted. So I don't know if the big tab is ground. Middle pin was V in, what I could remember from the schematic. So that's when you're assuming something actually can screw you over. You shouldn't assume ever if you don't know for sure. Just check the schematic and you won't screw yourself over. Because you could diagnose a part as faulty when it's not. Okay, so let's go over and check voltages now. As you can see on the image, it's not hooked up yet, but I'm hooking it up right now. Okay, and I'm a voltage DC up to 6 volts. That should be fine. This should never have more than 5 anyway. Okay, so let's see what we can find. So I'm on a ground point. Let's see, this should be 3.3. Oh yeah, this is upside down. So this is 5 volts, this is the V in. And the 3.3 should be in the middle. Yeah, so there's the 3.3. And it's okay, so the voltages are fine. So that didn't kill the actual chip. So the chip most surely died to heat not being dissipated correctly. I'm just checking with the thermal camera to see if it's generating excessive heat, the regulator. But you can see the average temperature on the, up to the left, and it's about 32 degrees. So, and considering it's about 27, 28 degrees here in Canarias, that is pretty low. It doesn't generate a lot of heat. Of course, if you have it hooked up and with a HDMI signal, it will go up quite a bit to about 50, but still not enough to actually bother the PCB. The thermal camera is a really useful tool. Thank you for watching until the end. I'll be back shortly with another video. I threw out my back again, so I haven't been able to make videos for a short time. See you on the next one, guys. Bye.